Let us discuss an example on quotient rule. In our previous class, I discussed how we can derive the general equation for quotient rule, where I said that this quotient rule. Remember, I said that the y dx under quotient rule is equal to v du dx minus u dv dx all over v squared. So if you're given a particular function, the first thing you have to do is to take note of your u and v variable. For instance, let us take this example. If you're given the function y equals sine theta over cos theta, and you're asked to find the y, the x, that is the derivative of this particular function. Now what's the first thing to do? I can make the numerator to be equal to u while the denominator will be v. And from the general formula, we're told that the y dx under quotient rule is equal to v du dx minus u dv dx all over v squared. So since we know that sine theta is u and cos theta is v, therefore I can say that we have cos theta, v du means keep v constant and differentiate u. Is that okay? Then from our standard differential, we're made to understand that sine theta equals cos theta. So we have cos theta times cos theta, then minus, keeping u constant, we have sine theta into differentiating cos theta will give us minus sine theta, then all over cos theta all squared. Now since we have this, it is very easy for us to move over to the next step, which is to multiply through. Cos theta times cos theta is equal to cos square theta. Then we have plus sine theta times sine theta is also equal to sine square theta, which is all over cos theta square will give us cos square theta, and this is the y dx. Remember, we are differentiating the function sine theta all over cos theta, applying the quotient rule. What then would make us to know if we are to apply quotient or product rule? The first thing is to note that when you have the function in this form, y equals g of x all over f of x. So if you have something like this, then you should know that the rule to use is called the quotient rule. So moving further to what we have, we know that from our trigonometry, we're told that sine squared theta plus cos squared theta is equal to 1. This is from our trigonometric ratios. If that is said, therefore, we can deduce that this equation over here, this function over here, can be seen to be dy over dx is equal to 1 over cos square theta. And how is this so? Let me bring you back to what we have in the previous slide. We have that cos square theta plus sine square theta all over cos square theta. So if I split these terms, we have cos square theta over cos square theta plus sine square theta over cos square theta. But why do I have to go through this, since I already know that my cos square theta plus sine square theta or sine square theta plus cos square theta is already a function which is equal to 1. So if I put this inside, I would have that my dy dx will give me, dy dx will be equal to 1 over cos square theta. Now, I would also want you to recall that 1 over cos theta is equal to sec theta from our standard differential table. I said that in my last class. under the standard differential table that 1 over cos theta is sec theta, and sec is the short form of secant theta. Is that okay? So if 1 over cos theta equals sec theta, therefore 1 over cos square theta will be equal to sec square theta. And that is why from our standard differential table, we're told that sine theta over cos theta definitely from trigonometry equals tan theta. And the differential of tan theta, that is dy dx of tan theta, is equal to sec square theta. And that has been proven by our derivation. So this is where we'll end it in this class on the derivation using the quotient rule. In our next class, we'll talk about the chain rule. Do not miss it.